Is there something that links relational databases, functional programming techniques, and entity component systems from the game world all together in one place? Because on the surface, it seems like they're all quite disparate ideas. Well, about 18 months ago, we had a guest in, Tyler Cloutier, and he was either very good at seeing the connections between these sorts of ideas, or he was a little bit crazy because he decided to create an MMO, massively multiplayer online game. And he decided that the best way to create one of those was to build a new kind of distributed database from scratch. That sounds like two of the hardest projects you can take on. And he was doing them both in parallel with a fairly small team and a fairly small development timeline. It sounded crazy, but the more he explained it, the more I thought he was onto something. At least in theory, that didn't guarantee it would work in practice. Well, roll forward 18 months, the game has launched with a few lessons learned, and the database itself is becoming both the heart of the game and the heart of the company. So, what ties those ideas together? How does it work? And what were the lessons learned? What was the gap between theory and practice? But more importantly, by digging into it, how can we begin to see more systems as kind of massively multiplayer online games? Maybe serious games, but still massively multiplayer. Somewhere between game architecture and database architecture, is there a more universal architecture we could learn from? At the very least, SpacetimeDB and Tyler's perspective on software are a very interesting point in the design space. So let's go and explore it. I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Tyler Cloutier. Joining me as a returning guest, the brain behind SpacetimeDB, it's Tyler. How are you doing, sir?
I'm doing very well. Thank you so much for having me.
I'm glad you're back. I really am, because the last time we had you on, you were looking at both a database launch and a game launch. And I was genuinely wondering how well that was going to go.
Yeah, me as well. I appreciate being back on. It's been a wild ride. I expect it will continue to be a wild ride. But yeah, it's always going to be exciting when you decide to write your own database just to be able to write your own game. And that has not disappointed.
Yeah, well, now I've played the game, I know you're not completely mad for doing it that way. And you must feel reassured that you're not completely crazy either, having launched it, right?
I do. I think, though, at some point in the development of it, it became so retrospectively obvious that it was a good choice that even before we launched the game, we knew we were onto something. What I think is different is that once you actually get it out there, you really know for sure that the performance is not a pipe dream, but it's actually something that can support a real-time game.
Yeah, because we talked a lot about the potential performance traps in there.
Right.
But before we get into it, I think, because it was a long time ago, and I'm sure not everyone has listened to that episode, give me a recap on the basic architecture of SpacetimeDB. What is it that you're trying to do that other people don't do with databases?
Yeah, it's a great question. So let me give you an idea overall of what SpacetimeDB is. So SpacetimeDB probably should be called Spacetime OS. That was something I sort of left out towards the end of the last one. But essentially what it is it's a database, a distributed database. You take your program, you compile it to WebAssembly, you upload it to run inside of the database, and then clients connect directly to the database. They call functions on the database, and then subscribe to data, which gets updated in clients in real time. And so the reason I say it should be called an operating system is because it's essentially a system that schedules your program, runs your program, and then persists data to hardware and sort of manages all of your hardware together in a way that you don't have to care about, which allows your program to run and then clients to connect to it, essentially.
And when you say you are uploading your program to the database, that's you as like for instance, the game developer. But there's also a certain amount of computation happening on the client side, right?
That's correct. So the game developer is going to upload the main portion of their program to the server. The client is essentially a read-only replica of the database. But the difference is it's not a full replica; it's a partial replica. So you are sort of going to say, "Hey, I have X number of tables. I have X number of rows. In those tables, I am going to select some of the rows in those tables from some of the tables, and I would like them to be replicated to my local client as quickly as you can, and then kept up to date over time." And so that's what the client is doing. And then obviously the client does an additional amount of things on top of that. In games, for example, anything that doesn't need to be synchronized across clients, so none of the multiplayer stuff. So if you have like particle effects and things like that that are just purely for visualization, that's all done by the client. Animations at times. A lot of it is triggered by things that are on the server. So if there's an explosion that everybody needs to be able to see at the same time, that gets sent down as a piece of data, and then the client renders that. So the client is doing the rendering. The server is doing the sort of source of truth of the data in your application.
So the server projects out a subset of the data to each client, and then the client projects out a visualization of that subset to the user.
That's exactly right. It's very functional programming in spirit.
And remind me about writes, because if I'm running a game client, I want to write my new position, say, back to the server, but I also want to immediately visualize that change, right? And you've got collision detection on that, so there is logic over whether the write can happen at all or not.
That's right. So in our game, in Bitcraft specifically, there's not a lot of collision detection, but there is some. So a lot of games have more. If you're doing a first-person shooter, you have to be very careful about timing, and latency matters a lot. Different games have different sort of latency requirements. But yeah, so generally how this would work is through something called client-side prediction. So that is my client is going to, it has a replica of the world. So it knows where things are as of a certain point in time in the past on the server. And it will look at the world and it will say, okay, I know what the server will do because I know what the code and logic of the server is. So I'm just going to do it locally, assuming that the server is going to say that's okay. Then I'm going to also send it to the server at the same time. So locally, I'm rendering it as though it has actually happened in the server. It hasn't. I send it to the server. If the server eventually comes back and says like, yep, that happened, no problem, then the world has proceeded as I have predicted. And it looks the same, and I just kind of throw away, in a way, what the server does. Now, if I send it to the server and eventually it comes back and the server said like, whoa, you can't do that, I will have to go back in time on the client and undo what I had done and sort of replay forward from there. And so that's what client-side prediction is for games.
And is that done... Is the reason that works is it's probably done on a matter of sub-second intervals. So at the worst case, I can just sort of jump the player's avatar.
I mean, it depends on what your latency is and how much collision is going on and so on. It can be a more or less good experience. But yeah, generally speaking, this is, from you to the server, something like 100 milliseconds in a relatively bad case. You're doing this in real time. You can see like this will be scenarios where people kind of pop back around in different regions. If you see that like in a game where they like rubber band and stuff like that, that is often a cause of rubber banding.
Yeah, I've seen it a lot more with other players not being where we thought they were going to be than with my player, right?
Well, that's right. Well, yes, true. I mean, it's not so frequent that you will invalidate what you did, but it can happen. I mean, you can imagine a scenario where your client believes that you killed somebody. This is actually a long topic of discussion to get into, but there's some legendary talks that people have done at GDC, for example, about like how I remember this one specifically from Overwatch about how they do the client-side prediction on their end, and it gets very complex because you also want to do different techniques, like, for example, lag compensation, which is you might actually... Okay, let me give you the example of where this can go wrong. So if I shoot you, and my bullet goes out, and I think it hit you, but actually, although on my client you were going in front of the bullet because you kept going, you had actually turned around, and I didn't know that yet.
Right. So I dodged, but you didn't know.
Correct. I dodged, but I didn't know. My client will. What will happen in certain games is it will animate the bullet collision,
Mhm.
so you'll see like a blood spatter or something, but actually you won't die because they don't actually compute the die until the server actually says for sure you're dead. That's to avoid people like dying and then coming back to life again.
Right.
So there's sort of advanced techniques that you would want to make sure you get right. And there's some very legendary talks about it. They do very fancy things, like, for example, they'll use UDP and they will put in the last 10 frames or seconds or whatever it is of operations, so that if you lose a message, the next message will have the message that you had intended to send, but that got lost. So you just sort of redundancy.
You've got like a rolling window of what's happening.
That's right. Exactly. And so it's a way of trading off bandwidth for latency. So you have to use more bandwidth, but you get lower latency because you don't have to retransmit.
Okay. We're going a bit too far into game development theory, and I kind of want to stay on databases. But you have hinted at this. It's like, from the client side, this is like an event streaming model. I get a subset of all the events in the system. As a client-side program trying to figure out what's going on, is this also like a functional? It's like a fold, isn't it? We're reducing over a stream of events to find out the state of the world at the moment.
That's exactly correct. And more than that, we actually have named the functions that you call on the server reducers for exactly that reason. So let me talk a little bit about that. So the security model of one of the first questions I get when somebody says, when I tell people that your clients are going to connect directly to your database is, was that secure, right? And reasonable question, I think, for the old permissions model and architecture of databases. But the thing that SpacetimeDB does is, because you're uploading your actual server program, you take all the same logic you would normally write in a regular server and you put it in your database. So it's not as if you're not doing all of that checking. You are doing it. It's Turing complete. You can do whatever calculations you want to. We're just taking it and sort of from a performance perspective, putting it in the same process as your database data. And that is important for speed and performance. You would not be able to achieve the types of things that you're doing. Those functions that take those inputs and modify the database state to produce a new database state, we refer to as reducers, because they're taking all actions and reducing them into the current database state and producing a new database state.
Right, yeah. And is it functionally pure? I mean, if you lost the database state, could you replay the event log?
Yes, it is. And so that's one of the most important components about reducers, is that they are replayable. So, for example, what we do currently do in SpacetimeDB is we actually store the set of changes that you've made to the database state on disk. But alternatively, you could actually just store the code as of that point in time and the input to the function, and you can just replay them and then actually get the same exact state that you would have gotten back in time. And that means managing things like access to random numbers, access to timestamps, anything that could potentially change that you would have to have as input into your reducer to produce things. But once you do that, you can start to do very, very cool stuff, which we haven't released to the public. In some cases, we haven't fully developed yet. But for example, a point-in-time debugger. So you could set your database state back to a particular point in time, start up the reducer as it had run at exactly that point in time with production data if you wanted, and then step through the code as it would have happened at the time that it did happen, which is pretty fun.
That's something I've used in Elm front-end language.
Oh, yeah.
Right? That time-traveling debugger thing. And it's really good when it works well, right?
Yeah, it's really fancy.
Now
imagine you can do it for your entire MMORPG, right? So somebody reports a bug, you're like, that shouldn't be possible. Let's go back to the point in time when it happened. Let's see what actually happened on the server.
And is this something you're actually using in production? I mean, have you solved bugs with that?
So we have not built specifically this point in time debugger. We absolutely have gone back in time to the commit log and looked at the changes that a particular transaction made but we haven't built the thing that actually steps through your code yet. That would be super fun.
Oh, right.
We haven't done that yet.
But yeah, but you've got all the data. So you haven't got the nice UI on top of the basic principle.
Correct. That's right.
Okay. So we should talk about. God, there's so much to talk about in this, but I think we have to now get into. You were just about to launch last time we talked. You've got this database. Right. You've built a game on top of it, an MMO, and then you were just about to launch. And tell me about how the launch went, because I know you had some performance problems. So did it go well overall? What did you learn that you should have done differently before you released?
Yeah, so for people out there, the game is Bitcraft Online. You can download it on Steam. It's in early access. And it's an MMORPG. Just to give a brief idea of what the game is overall. You start in the wilderness in a shared world with all the other players, and you rebuild civilization from the ground up. So you can edit the terrain, you can cut down trees, you can build buildings, you can level your character up. It's similar in concept to RuneScape plus Minecraft, if that makes any sense. Yeah. And in June of this year, we went from our alpha phase, which was sort of a single region and a small number of players, into Steam Early Access, where anybody who bought the game could get access and play the game. And shortly before that, we released SpacetimeDB into 1.0, because if we were going to use it in production, we felt that it was ready to be used in production. And we've been working for a while on getting it to that state. And then launching the game into early access was very interesting. Prior to that, we did a preview on Steam, which is like you could get access to a playtest of the game right before early access went out. That was interesting because we discovered during that, either it was during that or actually in early access, I think it must have been in that preview, we actually discovered that our hardware was bad, which I have, as a software engineer, have been trained to never blame the hardware.
Yeah.
It almost never is the hardware. But in this case, we saw 2 of the regions. So we had 9 regions in the game, and each region is managed by a SpacetimeDB database, and that handles all the players in the region. And as they move between regions, we move the data from one region to the other.
Okay.
Just sort of a way of sharding it spatially so that you can get more players into a single world. Mm-hmm. And we saw 2 of the regions were lagging quite badly. And this was during one of our tests with players. We thought, well, that's just, I thought that was suspicious, but we thought, something's wrong with our software. We'll look into it more. We couldn't figure it out. We said, all right, well, we'll see what happens again. Well, in either the preview or the early access, I don't remember which one, we saw the same thing again, just 2 or 3 of the regions really suffering. So eventually, after much debugging, we ran like a basic Intel benchmark, and 2 of the nodes, or 3, I don't remember, were doing like 25% of the performance on the CPU benchmark that the other 2 nodes, the other nodes were doing. So we swapped those out. We migrated the data over, and bam, it was going great. So that was interesting. I've never had that before.
I mean, I've been in a situation like that once before, and you have to check a heck of a lot. You'd end up checking a lot of things before you start suspecting the CPU.
Absolutely. Yeah. I mean, yeah, it's one of those things where it's like, is it going to be the CPU that everyone is using that you think you would have heard about this problem, or is it going to be your crappy software? Yeah. 99% of the time. Yep. It's your crappy software. But in this case, it was not. So that was interesting. I don't remember if that was in the actual alpha that we did the swap, or it was the test right before. But that was a shame, because it sort of made it seem as though we didn't have our stuff together when we did. But it turns out we didn't fully have our stuff together, because when we actually then released, we still had performance problems. So we resolved the hardware. We're still having performance problems. And we had to figure out what was going on over a period of like 24 hours. So this is like prime time. When you launch a game on Steam, you've got one chance to get it right, because people are going to leave reviews immediately, and those reviews are permanent.
Yeah.
And if they can't play the game, they're going to leave a bad one, and that's what you're going to have to
You're
be stuck
stained
with
for life,
forever and ever.
right?
So this was an absolute race to minimize the number of negative reviews. So when we put it out there, I mean, the game worked. It wasn't as if it didn't work, but I think somewhere around like 500 to 700 people per region, we were starting to get like enormous amounts of lag. The worst one was like we had like a minute-long lag spike on particular regions. So some regions would just start taking a huge amount of time, like full server freezes. Nothing was happening. Everything was dead for like a minute,
Right.
which is a very, very long time in computers. In fact, it's so long of a time that it's like something is catastrophically a problem. A lot of times computers take seconds. That's when something is broken. Like things don't take seconds in computer land unless something's broken. If it's minutes, there's a disaster happening. And that actually turned out to be the case. So one of the things that we noticed was this would everything would be fine. And then after a period of time, it would get bad, and then it would get bad, and then it would get really bad, and then we'd get these big freezes. What we discovered actually was what was happening is we had an AI agent that was listening to the game state of the world, and periodically it would crash because there was a bug in the external client. And it would disconnect. It would disconnect a lot of different agents all at the same time. And we were logging something an enormous number of times when you disconnected. That is to say, all of the messages that we had not yet delivered, we logged once per message.
Right.
So if I was a slow client and I had accumulated a lot of messages, I would be disconnected, and then we would log something about that message every time. And moreover, that log still happened, I believe, while we held a read lock. So it would take more time, which, by the way, would cause other clients to build up a queue of messages. And then when they disconnected, because they were so far behind, they would print a lot of logs. And then the printing of logs would cause more people to disconnect, and there was a sort of cascade. And so you'd see, like, it would get worse, and then it would get really worse, and then everybody would freeze and disconnect, and then it would start be like kind of okay again, and then it would sort of get bad. And so that was very interesting. And so we should have been logging asynchronously, in this case, but we were not. Actually, we probably shouldn't have been logging what was essentially a trace message in debug.
But that's exactly when you launch, you want that kind of level of debugging, but
you do. And I think these are the types of things about performance that people don't really think about. Like, you think about, memory allocations and caching and all that stuff. Yeah. Even if you get all of that done, like a log in the wrong place at the wrong level while holding a lock can just sink you.
Yeah.
So that was one thing that went on. There were a couple others. I don't know if you're interested in the further details of what went on there.
I mean, I can see how, like, things like there's always fundamental performance, like is this constant time, or is this order n squared, right? And that you can't fix unless you go right back to the drawing board. And then there's that incidental annoying stuff like logging messages need to be asynchronous, and that you fix, I'm assuming, fairly quickly, and then you suck your wounds and learn, right?
Yeah, we had that fixed within 4 hours. There were within 24 hours. There was 4 problems essentially. The first one was there was a workload that was different in production than was either in our test cases or in our alphas, and that had to do with the multitude of regions. So in the large number of regions that we had, when you opened a UI element, which, by the way, our bots didn't do. So we had like load testing bots. They would walk around, they would pick things up, they would mine things. They never opened any UI.
Oh.
And when you open the UI, we would do these one-off queries to get various data from the thing. So this is not a subscription to the data. It's just like, hey, I don't want this data long-term. I just want it for while you have your UI open. So please get me the data.
Right.
And we'll do that. So we did that. And in specifically the large full world, we had map locations. So when you opened up the map, or you opened up certain like trade windows and things, we would go get all of the data. And there was a set of queries that were not optimized. We just, like, the optimizer just didn't optimize those particular queries. And So they would scan a lot of rows. And we did not notice this in our bot testing on the full world because they didn't open the UI. And we didn't test it in the alpha or the preview because we didn't have as many regions. And we sort of had 1/9 of the total amount of actual UI the things that we would need to render on screen.
Okay.
So that was something when we went live, immediately we started to see this. And we started to see, especially in the tutorial where people are opening up all the windows, having a lot of performance problems there.
Right. Yeah.
So that was interesting. We added the optimization for that kind of on the fly, and then just published the new database, and that started working fine. And then there was the disconnection and the freeze issue that I talked about, and that led to a thing that we called Region 8 disease, which is where Region 8 would start getting bad, and then it would get really bad, and then it would be very, very bad. And then the final thing is that we had detected some of these freezes before launching, like the night before or like 2 nights before. And the thing is, with Steam, is you've set your date. So there is no changing the date because you have to get approved.
Oh, yeah.
So you've just got to be ready for when it's happening. And so we had to be ready. We saw these freezes, and we rolled back to an earlier change because we thought they had been introduced, but they actually hadn't been introduced. They were always there. It was just under certain conditions, the mob monitor would crash and cause the cascading logs problem. And so we didn't ship with a set of optimizations on queries that we should have shipped with. And so that final one, we applied that, and you could see our graphs go from way up here, just whoop, and then they would be super low and very quiet. And so after about, I think it was between 24 and 48 hours, we had resolved all of those, and it was relatively smooth sailing.
Okay.
After that point.
That raises a whole bunch of questions, but I'm going to ask first for the big picture. Since that launch, and you've got actual traffic coming in, how has the database fundamentally performed?
Well, since the launch, it's been fine. Certainly for the game, it's only gotten better, right? So as an MMO goes on, typically it comes down, you release an update, it pops back up, and then it comes down again. So we've had a steady but slowly declining player base since then, and performance has been great. We haven't really had any problems with that. What it has led to is us looking into and using more so some of the other features of SpacetimeDB. So, for example, one of the very cool things that we can do with SpacetimeDB, because we have the whole server logic, is we can actually swap the server logic out at runtime while all the clients are connected and not disconnect any players. So if we have to do maintenance on the server or change the logic of the server, we can just do it, and no downtime is required.
How's that working? You're capturing an event log. You've got the state of the world. What do? You introduce new code and hand the state of the world off to a new process?
Yeah. So what we do is you upload the new program to the server. We let all the existing transactions finish. We swap in your new logic, and we start the next transaction, and off it goes. So the key ability for us to do this is that we have distinct periods of time when, in between when you're running code, right? We can. It's not as if you're just running code all the time. You're doing transactions, and so we can say in between transactions, we're going to swap out the code, and then as long as the clients are still compatible, so all of the API is the same, or you haven't deleted things that you like functions that they're calling, they will be none the wiser. So you can change things like the physics of the world if you wanted to at runtime in between transactions without disconnecting clients with no downtime.
Okay, the thing I'm not quite understanding there is maybe I'm coming with assumptions from how reducers normally work in a functional programming language, but
Sure.
do you have to serialize the state at the end of the transaction, save that so that the new code can pick it up and know where we were?
Yes and no. So the first part is true. We do serialize that. We put it on disk so that we can recover to the state that we need to as of that particular transaction. But we do not use that state, those sort of diff states, to have the new state be applied to the database. So what do I mean by that? In a transaction, you're basically inserting rows and you're deleting rows. We record all the rows you delete and insert, and we write them to disk. We also just apply those changes directly to the in-memory representation of your tables immediately. So I shouldn't say immediately. It's staged, and then when you commit, it's applied. And that is important so that you can have atomicity, so you can roll it back if you don't actually apply
Right.
it.
Yeah.
And so that's how that works. But fundamentally, you are correct. The reducer produces a set of changes. Those changes are applied to the current state, and they're also written as changes to disk.
Okay, so there is an in-memory database which the new code will just connect to.
Correct.
Okay,
That's right.
so it's the in-memory database that is that state that gets passed between iterations.
Yep, your tables are represented as in-memory tables, and you access them. It's a key component of the performance. So we can do things like physics calculations, and like I have a demo that I can run where you have a bunch of balls all bouncing around and colliding into each other. That's all happening within a transaction. Each frame running within a transaction, doing all the collision logic, and then returning all the changes of positions of all of the circles, and then we write all the changes to disk, and we go to the next transaction.
Okay, then that begins to explain something I didn't understand in something you said earlier. You had some queries. One of the reasons you had performance problems is you had some queries that weren't optimized. But I mean, what's that look like if all the data is basically in memory because you're not indexing?
Yeah, so I mean, unoptimized queries can be this. So in the game, there are location states, and the location state is just. Let me take one step back. So, how do we represent data in the game? We basically use the entity component system model, which is very similar for Bevy, but it's ECS is sort of a subset of the relational model. So, the relational model is ECS plus more. And
Okay.
what I mean by that is I can build an ECS inside of Postgres. And that is as simple as saying I have one table, which is the entity ID table, and I will have one column, and it will just be all entity IDs. And I will have other tables, which have a foreign key reference to the entity ID table. So, for example, I might have health being a table, and I might have like combat stats being a table, something like that.
Yeah.
And then for any entity that I want to give the property of health to, I insert a row into the health table that has a foreign key relationship to the entity ID. And now that entity has health. So I can look up all entities which have health and combat stats and food or whatever it is that I want to apply to this thing, and I can look that up. So that's how we represent data in the game. One of the things that we have, one of the components that we have is a location state. So those are things in the game that have a place in the world that is fixed. So a tree, a building, things of that nature.
Right, yeah.
There's about 20 million of them or something thereabout in each region, if I'm not mistaken.
Okay.
And so what you can do that's wrong, if you misoptimize your queries, you can say, okay, I would like to get all, let me see if I can come up with an example. I want to get all resources nearby this player or something like that. And so what you can do is, and maybe there's only 10 of those, or let's say 100 of those resources in the world. What you're going to want to get is also the location of those resources. So what you do is you say, okay, I would like to loop over all the resources of this type.
Yeah.
And for each one of those resources, I'm going to scan the 20 million rows of the location state to find out where that resource is. And I'm going to look it up by its entity ID.
Right.
And so that's a lot.
Yeah.
It's 20 million times 100. And so if you're not doing it, the way you'd want to do that is you'd want to have use the index that we already have on location state to say, look up the location state by the entity ID rather than scanning the full table. Or actually, I said that backwards. In some cases, it is even worse. In some cases, you will scan the entire location. You'll go location by location to see if they have if they have a resource in the resource table. So you'll look for every location, try to find if it has a resource in the resource table, and that's looking through 20 million things when you really only had to look through 100.
Right. Yeah.
So there's many various kinds. You have to use the indexes that you have, nice, okay. And then you have to also I forget what the particular name of the optimization is, but you have to decide the join order so that you are ordering your joins to do the smaller things first.
Yeah.
You don't want to you want to eliminate, or you want to apply your where clauses in a sense before you just go to town.
You are being
and that's what we're not doing.
Human equivalent of a query optimizer in a database that's had 30 or 40 years of engineering to it.
Exactly. And that's the beauty also, I suppose, of query engines is you do not tell it to do it a certain way. You simply tell it what you would like the results to be, and then it figures out how to do that. The thing is, it's only as smart as it is, so you need to always kind of improve it. And then it leads to the classic database problem of like, oh, I didn't have an index on that column, and now it's slow. It's as if you wrote instead of a hash table, you just had a big array.
Yeah. There's no getting around those fundamental data type issues, right? Yeah,
there is not. But I think one of the really cool things about this architecture for how you represent in-memory data is that changing the physical representation of the data is just configuration. So you add an index here, you remove an index there, you can change the optimizer to do all these cool things. But the logical model doesn't change while you're doing all of that stuff. So you are accessing the data in the same way that you were. You don't have to rewrite your program to change the performance characteristics of your program.
Yeah.
And decoupling those things was the original motivation for the relational model in 1970.
Yeah. The way the data is stored shouldn't be the way the data is used shouldn't determine the way the data is stored, because you need to be more flexible than that, right?
How it's stored and how it's accessed. I'm sure you've had the classic problem, which is you have a list of things and they're in a hash table, right? You have a hash table,
yeah,
and it's keyed on like the username or something like that, and you're like, gee, I really would also like to key it on their first name or something, and now you have two hash tables and you have to keep them in sync. And so you have that sort of classic problem where it's like, okay, now every time I do an operation here, I have to make sure I do the operation there. And that is what a database can do for you. And then you can add or remove different hash tables as you want. And your code doesn't have to be rewritten every time.
But did you end up doing, like implementing all those algorithms to basically build an in-memory database from scratch? Like the internal in-memory database, is that built from scratch? Or are you leaning on... I don't know what. I'm sure there are off-the-shelf in-memory databases that you could have picked.
It's a good question. Not so much. So we don't use anything internally. It's hand rolled.
Okay.
If I knew, I don't know that that's a great way to go. I think it. I think it has upsides and downsides. So the upsides are you fully understand it. Like you don't want to fall prey to the it wasn't developed here disease.
Yeah.
But at the same time, there is a very strong benefit to having a full understanding of the system and the ability to change it for the particular workload that you have. Because that can make an enormous performance difference, as we've found. And so it was too much of a risk for us to say, like, all right, we're going to go tinkering with somebody's thing. And then, actually, we didn't understand that this was the assumption that person made, and it doesn't quite work for us. So we just built it ourselves. It's not really that complicated in a way. It's just sort of a way of organizing your program memory, if that makes sense. And what I will say is, like, from the module as of today, the way you access the in-memory data is through what we call physical queries. And those physical queries are not through the query engine. So from your module, like the internals of your database, your program, your server, you do physical, like what we call data store operations. So the data store is the thing that is the in-memory data structure that holds your data. And you can do things like, I would like to use this specific index to look something up, or I would like to scan the table, more or less. That's to be distinguished from the clients subscribing who say, I would like to run this query, and then we optimize the query for them. But we give the power for the server writer to do whatever order of specific physical operations they want. Very shortly, we already have to some degree. We also want to provide that query engine to the server writer, so that they don't have to care about the particular operations that are done physically. But they can kind of rely on the query engine to do that, or they can, of course, just drop it down to the physical layer and say, like, no, I want to do these particular operations.
Right. So does that mean that as a writer of a program for SpacetimeDB, I am... What's my language there? Is it an API? Is it two APIs? One that's low level for memory structures and another one that looks like SQL?
Yes, that's essentially correct. So we have a query builder, a typed query builder that you can construct queries, and then you can send them to the engine, and then the engine will return the results, and they will be typed as well because the query builder is typed. So you can say, um, select. It looks like SQL. It looks like an ORM in the
Okay.
SQL Builder
Yeah.
version of this. So you basically say, select from this table where this, join this other table, and then we know the type of it because that we've built that up in the query, and then we can say, hey, here is your this row and your that row, and then you have them in your module. Alternatively, if you want to use the physical API, you can say, I would like to iterate this table, and so it'll give you all the rows in that table just as you asked for. You can also say, I would like to, so you can do like the way you access all of the data in the database is through a reducer context, which gives you sort of access to the database. So you hit CTX, which is the context, .db. Then you would say dot your table name, so like dot player.
Yeah.
Then you would say, if you had an index on a particular column, let's say it was the ID, you would say dot player dot ID dot find, and then you put the value in.
Okay. Yeah.
If it was a range query, you'd say dot filter, and you'd provide the range, and you would get the values within that range.
Okay. Yeah, that makes sense. Also makes sense that maybe you wouldn't go to writing actual SQL because you want to keep that type information within the compiler,
Well,
right?
exactly. So that's actually the tricky part. The clients currently write SQL, like string. And that is fine. It's not really very complex SQL queries. But we are also going to be adding the type query builder to the client because why not? We have it. We're going to be building it for the server, so why not also have it for the client? And that way, people can just get they can construct their queries of the right type. Right now, we do return queries typed, but that's sort of relying on you putting the right table name into the query.
Right. Yeah. Okay. So from there, I kind of want, because we've got this dichotomy, or hopefully symbiosis, of you building a game and a database, right? But if you're really a database company while you're being a game company, something about the way you said ECS made me think, well, is this database just useful for game-like things? And is that fine?
Yeah.
Or do you think the model applies more broadly? Do you have ambitions to be a generic database?
This is a very interesting question. What I would say is actually we are fully a relational database. There is actually no feature in SpacetimeDB that is specific to games at all. It happens to be that the ECS model is essentially the relational model. There are other reasons you would use the ECS model in games, which is the physical representation of the data, and the way that games typically query those things can be very well optimized for the current hardware and caching and stuff like that. But the actual model is, in some sense, the relational model. They are one and the same. And more ECS systems have recognized this and started building more and more powerful query engines. And the one I would call out is Flex, FLECS.
FLECS.
It's written in C, I believe, C and maybe C++. And they are adding additional query capabilities to that. But to your point about, is this specific to games? It certainly is not. And in fact, we're making a big push into web. So we've just added TypeScript support on both the server and the client. So you can now write in SpacetimeDB, as of this moment, TypeScript server modules. And we think this is actually extremely powerful for web in a way that I think really has not been explored. And one example of how I would say that's true is it fits really into the modern web frameworks extremely well. So something like React, actually the name Reducer was originally inspired by React Redux, which has the concept of reducers. In fact, React has a use reducer hook that is conceptually very similar to SpacetimeDB. And what you can do in our React library that connects to it is you can just say in your component, as though you were saying use effect, you can just say or use state. You would say use table. And what we will do in the background is using just our regular sort of TypeScript SDK, synchronize the state of your table with the particular where clause that you want into your React state. And then anytime those results change, we re-render your React client. And so having a real-time, and I mean real, true, honest to goodness real-time React app is as simple as saying use table and use reducer. And use reducer is a function that you can call that will cause tables to change. And that's literally it.
And presumably from what you've said so far, when the server says that the table has changed, you are just shipping the individual rows over the network. So it's bandwidth efficient.
That's correct.
Too. Right. And then when I, as a user of that web page, do something to a particular table row, you're going to treat it just like the collision detection thing you were talking about. You're going to optimistically say the table has been updated, send it to the server, and if the server rejects it, it will reject my local change.
So that is correct. We don't. I just want to be clear. We do not currently do that in the TypeScript SDK, but there's nothing preventing us from doing that. In fact, if we were to take the database engine and run it in the client, you could do all of this stuff like incredibly real time, where it looks as if you're interacting instantaneously with the server. So the server is locally, and we're actually making changes. And only if there's a disagreement do we roll anything back or say that like, hey, you can't do this transaction because X, Y, or Z happened. So you tried to transfer out of this account into another account, but you had already done it in another tab. Right. You would want to do that because you don't want to say like, yeah, it's great, it works great, unless that actually is the case.
Right. Yeah, I think because I know we touched on this the last time we spoke, but I know people are going to wonder. So I think I have to get you to recap the security model for this. Because if I'm running essentially a subset of the real database on my machine, it sounds like a security hole on the surface.
So I guess there are a couple things to think about. So assume we're not doing client-side prediction, just in the first case. We can always add that in. If we're not doing server-side prediction, what we have is almost the exact same model that we have today. So you have your server, you have functions you're calling on your server. They're just RPC calls. There's nothing really fundamentally different about that. Those RPC calls do authentication. They do authorization. So we're OIDC compliant. So that's OpenID Connect. So the thing that you see like sign in with Google or whatever, that's all something we support. So your users authenticate with SpacetimeDB. We then send your module that you wrote, like, hey, this is the ID card, more or less, of this person who is connecting. You do whatever internal logic you would like to do to decide whether or not they can make a change to the server or not. And then if you say no, by the way, you just roll everything back, and it was as if they had never been there. So that's even more secure than it currently is, because what can happen in regular servers that aren't transactional is you can throw an error in between transactions and half the thing has happened or something. Like malicious people can kind of mess with your database state if they know how things work internally. Or it's very hard to guard against that because you need to make sure that your error boundaries are right and you've got your transactions all set up, and there's performance considerations because now if you're doing very long running transactions, you're locking rows and all that stuff. But otherwise, it's quite the same. And then on the read side of that, you can have private tables. Those are just not visible to anybody outside of the database. You can have public tables. Those are visible to anybody. And then what we have now, which I only talked about theoretically last time, was the concept of views.
Right.
So a view is a table that you construct with a procedural function inside of the module, and you return rows from that. And then it looks like a regular table, but it's actually constructed with your procedural code. So you can also do whatever arbitrary logic you want to do there. So for example, I can say, this player, let's say I had an inventory table or private or a DM. Let's say we're doing a chat app and we make a DM table. I can see in that table only things that were addressed specifically to me. So there's a 2 column. And what I do is I just return, I look up by the person who's calling the view, all of the rows in that table, the sort of the underlying private table that are addressed to my user, and I return those. And then those rows are sent to me and only to me, because anybody else would not have that same situation. And the better part about it is they're also updated in real time. So anytime anybody sends me a DM, it's automatically sent down to my client. And that's how we apply that.
Right, yes. And it's automatically parameterizable, right? Because I could do this in a regular relational database, but I'm not going to create 20,000 views for my 20,000 users.
Correct.
And I need something
Yes,
like low-level security, or I don't know.
Exactly. And we actually went through an experimentation phase with relative security, because there's some performance considerations with views that I can talk about. But yes, you can take a view. So a view is a regular function. You can pass in parameters. Your identity is a parameter. I think we don't expose like the timestamp, because you could do that, but that's like, well, now we have a lot of views. We have a view for every second. We return these things and we materialize it. So if anybody else wanted to query the same thing, so in this case, nobody else would be querying the same thing unless I had multiple devices all with the same identity. But in a lot of cases, for example, in games or in something else, you might have something like a leaderboard, and you want to compute that on the fly.
Yeah.
And everybody's going to be sharing the same view, so we will materialize that. And then if somebody else shows up, we just return the results. So we don't actually call your view again. Your view function, your view constructor function, or whatever you want to call that. And that really helps with performance as well. But yes, fundamentally, they are parameterized.
Okay. This makes me want to ask, because if this were any other database project, the next thing I would ask, which is slightly different because you've already written a game on it, but I would say, like, what about performance and what about network problems, right? If you've got 20,000 users collecting to their own subview and occasionally messages get lost, what's going on there?
Yeah, so this is the only benefit of having developed a full MMORPG just to prove out your database, which, I would not necessarily recommend, but it really helps us on performance, because we know without a shadow of a doubt that we can do these things. And so 2.0 of SpacetimeDB is all about we're coming to web, and we've been doing some profiling, some performance benchmarking against some existing databases. And it's really fast. So we're very pleased about that. I'm not going to share the numbers right now, because we're going to release them when we've got them solidly. But we can do multiple times more transactions per second for like a web workload. So imagine you have a bank or something and you want to transfer money between different accounts. One of the problems that you have in something like a normal relational database that you host separate from your server is that if you want to do a transfer, you have to get the balance of somebody in your server, look at that balance, get the balance of another person, look at that balance, make sure that they have enough money to do the necessary transfer, and then write both of those rows back into the database. If you're not doing that in some kind of stored procedure, or something like where you're preparing the full query and sending it over in one go, you're holding those locks on those two rows for milliseconds, like hundreds in a worst case, but like tens of milliseconds in sort of a normal case, or even, let's say, at least 1 millisecond.
Yeah, which means you either open yourself up to deadlocks, or you've got like a huge serialization problem on the entire transaction system.
You've got a huge serialization problem, and your transactions per second just goes into the floor. Consider, for example, even sort of a normal case for something like where you're tracking balances. You might want to have an account which represents all of the maybe you're making an AI startup, and you have a point system for like how much LLM juice you've used, right? So everybody's got a balance, and then you want to track like the total amount of balance used. And so you every time that you do an action, you deduct from their LLM balance and you add it to like total amount used, because you're doing double entry bookkeeping. Well, every single user that's doing any action is taking a lock on that summary account, the sort of the total used account. So now you've got this serialization problem where actually you can only do one transaction at a time, and each transaction is taking at least 1 millisecond. So you're capped out at 1,000 per second. That's just maximum you can possibly theoretically do.
Yeah.
Assuming that's happening. And so that turns out to be very, very slow. In SpacetimeDB, because you're in the same process as your data, and it's in memory, and it's just right across that WASM boundary, which is important for security purposes, but it's just right there. You're talking like tens of nanoseconds to be able to access it. So that's I suppose from milliseconds to like let's call it 1 microsecond. It's 1,000x performance improvement, right?
Yeah.
On the ability of you to get that thing and hold that lock for a very small amount of time.
And you have some numbers to back that up because games do these kinds of transactions pretty regularly, right?
Yes. Well, it's not so much that we're doing a performance benchmarking now, but it's not so much that it's that it's the only way we kind of have backed into it. It's the only way that you could get this to work for a game, because you really can't spend very much time on this. I'll give you one example of something that like people might not think about for performance profiling, or have maybe a different viewpoint on, that only through bashing our faces against it have we fully appreciated the importance of. Very commonly, for example, in let's say the web world, what you would do is you have an asynchronous scheduler. So in JavaScript land, it's single-threaded. You do sort of one thing at a time. That's actually pretty good. And it goes in an event loop, right? And so you get a request in that triggers a thing, you do a function, you do a callback, you return, and so on. You might think like, okay, this is really great. We're going to multi-thread the crap out of this. So we're going to take that thing and we're going to do a bunch of transactions all simultaneously, and we're going to return there. The problem is, if you're modifying the same data, those are being scheduled to different threads, because you actually are sharing a thread pool, and those threads are being scheduled to different cores. And now when you go to access your data, it's actually been modified on another thread. So it needs to be flushed out of the cache on that thread and loaded into the cache in the thread that you now have. And so you're sort of always operating only in L3 cache, which is shared across all cores.
Right. Yeah.
So L1 cache and L2 cache, they basically might as well not exist. Everything is in L2 cache, and you're constantly sending data across cores.
Okay.
From one to the other. Yeah. Not to mention things like false sharing, which is you appear to not be accessing the same data, but actually they're prefetching the data from one thing to the other. So if I modify, so like let's say I grab a collection of memory because I want to load it into memory, and another thread is modifying something that I am not modifying, but I have prefetched. Well, once they modify it, it needs to be flushed out of my cache, and now because I need to get the fresh data if I'm going to read it.
Yeah.
And so there's all of these sort of hardware things. So what we have actually found to be the most performant by a mile is single-threaded. Put it all on one core, one thread per core. Just you. This is your computer. You get the whole thing, and then just using L1 cache very efficiently, and that gets you way, way more performance.
Do you have a mechanism for set? Because it seems like you're wasting cores there, and that's becoming very important. Have you got some mechanism to say, well, these tables only live on this core?
Yeah.
Those tables only live on that. Can you shard tables up?
It's a good question. I guess what I would say is the naive parallelization thing that you could do, where you just say like, okay, throw a job over to this thread, do that job, and move it back and forth. You're constantly swapping between cores. We were in a situation where we were seeing sort of small transactions. They were taking like a millisecond. So we could only do like 16 in the time frame that you could, on the client, render a full frame with millions of triangles. So like something was not right. And it turned out that was L3 cache. This simple version of it is extremely fast. Could you do something more intelligent and say, there is no data sharing here, so I'm going to sort of load up these sets of tables? You certainly could. We do not do that yet. I think what we have learned is that you really want to suck all of the performance out of a single core and have a full mastery of how the hardware works before you even begin to think about multi-threading.
Yes.
And that's in a language like Rust, where we don't really have a bunch of thread synchrony bugs. which you would normally have if you didn't have Rust kind of protecting you from accessing things from different threads. So it's a very, I guess it's more advanced. People think of multi-threading as advanced. It's way more advanced than you would think. You can certainly do it. Will you get better performance? Probably not. The same thing that we've experimented with on the same vein is multi-version concurrency control. So are you familiar, I suppose, with multi-version? Or maybe I can give kind of a brief.
Yeah, I know it from Postgres, but give me your summary.
Sure. So the summary of multi-version concurrency control is I'm going to do a lot of transactions all at the same time, concurrency. And in order to achieve that, the transactions are going to look at multiple versions of the data. And the way that actually works, for example, in Postgres, as you're talking about, is when I make a change to a row, actually I will create a new row, which is only visible to my newly running transaction. And old transactions that are still running, instead of having to lock that row for that person to write on or something like that, I will just continue to look at the old transaction the old row that I was looking at, and my transaction runs, and I can sort of keep them in separate worlds. You get this version of the data, you get that version of the data. Actually, Git is an example of multi-version concurrency control. I have my local repo, you have your local repo. We have to do merge conflicts when we merge.
Yeah.
But I am operating at the same time as you're operating. It's sort of like slow human scale MVCC.
Yeah. I'd not thought of it that way, but Git is. Yeah, okay.
So it really is. And actually, our original MVCC model was inspired literally exactly by how Git works, where you have sort of like a main branch and you're appending transactions to it, more or less. And as long as they don't overlap, so if you didn't touch any of the files that I looked at, then we can't possibly have...
But Git has the luxury on conflicts of like, okay, that's a user problem. They can sort it out manually. You don't have that luxury.
Well, we we sort of have the ability to look at what your eyeballs looked at. So if the analogy would be, if you recorded every line of code that you saw when you downloaded it, if you didn't look at anything that I changed, then you couldn't have been influenced by my change in any way. And as long as you didn't write to anything that I didn't look at, we can sort of just merge these, no problem.
Okay.
But if we detect a problem, what we're going to do is we're going to basically say, pick one of them, and then have the other person redo their work on top of it, sort of like a rebase.
Okay, yeah.
And sort of now you can look at the things that I have done because I have done them first.
Okay.
We've decided the order. It's a little hand wavy because in code, like there's sort of long distance dependencies, but for a database, it actually does work. But it turns out, by the way, if you do all this, and I only know this because we have done all, if you're not very careful about it, the overhead of the bookkeeping of multiple versions can quickly destroy your cache performance to the point where it's just not worth it. It's just like actually just better to put those suckers in cache and just run over them one at a time. The old-fashioned way.
Yeah. It's funny. This constantly surprises me, and I remember talking about DuckDB, and it surprised me. But if you line things up for like the very core of the CPU and the way it's architected, you get such a performance boost that a dumb approach that way just blows a sophisticated approach that doesn't think about the hardware out of the water.
Yes, and so I think that the point there is not like could you get more with parallelization? Probably, but it's not the first order solution, or even it's like you really have to be very careful. But if you do, I bet you could get more performance. Not in all cases either. But yeah, it is such that like cache is king, as they say, and it can be 100 times faster if you're going to L1 cache instead of L3 cache. I don't know the particular numbers, but I'd be really interested in looking at the latency numbers. To give you a note, it's at least 10 times faster. I think we went from something like a millisecond per transaction down to like 10 microseconds.
Yeah.
So it's
a couple of orders of magnitude.
So that means I have to be running on 100 cores anyway to just get that same speed up.
Yeah.
And then you've got contention problems. So what if we just did them really fast? There's another database actually that has a very similar conception, and I give them all the credit because I think we believed that the numbers we were seeing come back, And we knew this was a good direction sort of because of them. And that is Tiger Beetle. So they have always had this philosophy, as far as I can tell, from the conception of the database. Single-threaded, they do like 1 million transactions per second, which means, by the way, you only have 1 microsecond to get them done.
Yeah.
And they just say, dead simple, write it in Zig, know exactly what you're going to do, no dependencies. We're gonna make sure it's fast. And I think there's something to be said for that.
Okay. Yeah. Tell me about.
And I guess the last thing I'll say there is there's also like you get the benefit of, hey, there's no contention. You don't get a performance degradation if you're accessing the same rows. In fact, you get a performance boost often because it's all in cache.
Yeah.
So you're good to go.
Yeah. Okay, but what about in the large? Because
Sure.
you've said that you've had to shard your game into multiple regions. There is a size at which you say, even under these wonderful performance conditions, it's so large, we need to split this onto different nodes.
That's correct.
So does DuckDB support that sharding natively for you, or is it something you had to write on top?
SpacetimeDB?
Yeah.
Is in this case,
what did I just say?
I think DuckDB.
Sorry,
but
I've got that loaded into L1 cache. I apologize.
Yes, fair enough.
Yes,
fair enough.
FaceTime
Similar. We all relearn the same lessons, I guess. So does it do it for you? Right now, in a sense, it does, and in a sense, it does not. But it's a very interesting issue. So, let's talk about, for one brief moment, I'm going to take an aside, if that's all right, to talk about what would be an alternative architecture. So, for SpacetimeDB, we load your database in memory. It fits on one machine. We put it in single-threaded, and you can just do the transactions super fast. All is well. What happens when your data is very large? So you just have a lot of data. So forget even about throughput of data, just like quantity-wise, it can't fit in memory. One thing that you can do is you can say, okay, well, I'll start caching it in memory only, and I'll write to disk, or I will write to object storage, and I'll pull it in. That's going to hurt your performance, obviously, because you need to go get it. But it's like sort of an L10 cache. It's very far away from the CPU, if you will, but the same idea otherwise. The alternative is to say, actually, what I'm going to do is shard my data across a bunch of different machines, and then sort of preemptively building that L10 cache. And then when I go to access that data, I will maybe pull it all into one machine. I'll run my query on it, and I will return the results or something like that. So that's something like, in the case of like NoSQL, something like Cassandra. In the case of like, I would guess what we call NewSQL, something like Spanner or CockroachDB, which are they can handle quite a lot of load. But you're always paying the cost of that L10 cache. It's sort of like, in order to do anything, I need to touch the network, right? So I cannot do a full transaction localized to one machine because by its nature, the data is sharded across. If I have one table, it's sharded across all the different things. Very important if you have a huge amount of data. But for almost any other workload, it's much slower because you don't have the data. So you have to go get the data, and you have to do the thing, or you have to ship your code over to the data and do it over there, or whatever it is. It's one of those two. And so for SpacetimeDB, it is always the case that we want you to be able to do certain transactions locally. We intend to probably relax that requirement. So you can imagine a new table in SpacetimeDB, which has a property called like distributed or sharded or something like that, where the latency of access goes way up because it's actually spread out over multiple machines, or it's partially cached in S3 or something like that. And you don't actually know, if you look up a row or you do a scan, is that going to look it up in memory? Is that going to go to disk? Is that going to go to the network? Is it going to go into another region? Who knows? So you certainly can do that same model. But for games, it's just completely untenable. You could never access that in sort of any of your hot loops. So what we do instead for SpacetimeDB is we give you, the programmer, the ability to shard the data yourself, so that within a particular module, you will always have the data that you need in memory. So what we do for you is, and this isn't released publicly, it's only something we use internally. Although you can actually, with a new feature, you can hack it into your own stuff. We do inter-module communication. So what that means is you can send a message from one database to another database, and we will ensure that the message gets delivered with exactly one semantics is the idea. So
I've got to pick you up on that. You can't say
Sure.
exactly one semantics is the idea. Do you have exactly once or not?
So in the internal, this is why we haven't released it publicly. In the internal version, it works, but it's not quite there.
Okay.
We want to release it publicly when we can actually do that, and we can. So exactly one semantics is very difficult to achieve. It requires that you remember all the messages you received, because you need to know: have I gotten this message before, or should I give it to them? So if you can verify that you have or have not gotten the message, then you can know whether or not you want to surface that to the application.
Yeah, you need idempotent
Fortunately,
delivery, right?
we're storing the full history of all the transactions. So we do have that information. And practically speaking, you have a cutoff on that or something. So it's if it hasn't gotten to me for a day, it's not quite exactly once. It's exactly once as long as it's not delayed by more than a day.
Okay.
In which case, you probably would get potentially more than one function call. And you can have that be configurable. You can say hey, look, I either want to hear about it more than once, or I never want to hear about it. That kind of thing. Okay, so that's so you can send messages. I guess, yeah. Do you have a follow-up question to that?
Yeah, because you've hinted at, and we have talked about this offline very briefly, but the idea of databases communicating with other databases. I know you have plans for the game where people can start to program their own space-time modules and upload them into the existing game.
Correct. And so they would be able to. I'll give you an example of how that's possible. So we have this system of being able to communicate with databases, which is not unlike the internet. You can sort of send a message to another machine. The only difference is each actor in this model, this actor model, if you will, is persistent. And so it has we handle the persistence for you and all that stuff. And you can call functions on other databases, more or less. And so what we could do, for example, in our game or in your application or whatever, is have a developer register a module with my module, the Bitcraft module, and I could delegate out to it various questions. So, for example, if I had an alliance system, I could say an alliance owner can create a piece of software that will vet new people who apply to join. So a player in my game goes up to the alliance board or building or whatever it is and says hey, I would like to join this alliance. Sends a message to the Bitcraft module. The Bitcraft module says, oh, this alliance, looks up its registry, has a module that determines whether or not this person should be able to join. I send a message to that module. That module looks at all of the data that it wants to about the game that it needs to. So is this player above a certain level? Are they friends with those people? Are they in that alliance that we don't want to associate with? Whatever it is they do. And then they send a message to the Bitcraft module, and we allow them into the thing, or we deny them as per whatever the alliance said. And in this way, you can sort of have applications that are not only sort of sharded or made of many actors, but made of many actors that are controlled by different real world people. And they can do whatever you program them to do realistically. And so that is why we do really think of the database as sort of an actor model system. And I think it's really a distributed operating system in that it's similar in some sense to Beam and Erlang and so forth.
Yeah.
But it also builds in the concept of, I don't need to trust. It builds in identities and permissions, which is really important if you don't trust everybody that's sending you a message.
Yes. Yeah. But it also builds in the idea of a persistent log of messages, which is something I've sometimes wondered if Erlang should have.
Yes, it does, and I think that's important. It's not important for just persistence, but also exactly one semantics and that kind of thing. And I think that's the thing that really makes them. I think it crosses. There's like a threshold where, if you can get across it, ops and DevOps and needing to be woken up in the middle of the night goes away. And I think that is, if you look at the cloud right now and you have Kubernetes set up, and maybe you get fewer alerts, maybe you get more alerts, I don't know, but one of those two, you cross a threshold in principle if you can get the system to manage enough stuff where you are not having to manage your infrastructure quite so much. The operating system manages your infrastructure for you, and you write your program. Now, that obviously does not solve you from bugs that you write, right? So if I write a module that gets into some kind of problem with the data, it's like, that's just what it is. I'm still going to get woken up for that one. If we have a gold dupe, for example, in Bitcraft, because somebody had integer overflow problems, which we have had, then that's just what it is. But I am hopeful that we can build a system where you don't have to worry about, like, it's abstracted over the machines, right? So, for example, you don't have to worry about machines failing and that kind of thing, which Kubernetes tries to do, and I think does do for the stateless version of it. But if you have persistent state, I have a stateful set here that's not replicated, I have to do all this. So then you combine it with database. So now you have like databases plus Kubernetes. If you could just get it all together and you have replication, then in principle you have sort of an unkillable operating system that's not localized to a single machine. It's a system that is distributed, a distributed system. And that's resilient. And so the dream is that your operations problems and your infrastructure problems can go away. And I would argue that there's one domain for which this is definitely true. Something like Ethereum smart contracts achieves that thing, right? If I were to write one, it's very expensive, it's very slow, there's a lot of other problems, but one thing you can say is that nobody wakes me up in the middle of the night to make sure that my Ethereum contract is running. And I think that's a very important property. So there is an existence proof that this is possible. We just have not achieved it for the cloud.
Yeah, okay. I always tense up when people mention blockchain-related solutions, but I will concede that feature...
This particular one.
Yeah. I would change the way it's implemented, but that feature is,
I would change it too, and I think we have changed it. But that one feature is true. It's very hard to bring down.
Yep, I have to concede that. So does this mean you've thought about replication?
Oh, yes. We support replication in the SpacetimeDB cloud version of SpacetimeDB. So SpacetimeDB comes in two flavors. SpacetimeDB standalone, which is available on our GitHub. And then we have the sort of more proprietary SpacetimeDB cloud, which is a clusterized version of SpacetimeDB. And it schedules all of your databases to various nodes and then does replication between those nodes.
And the replication, basically, because it's a write-ahead log-based system, you can just copy it.
Correct.
Okay.
Yeah, it just uses that.
That makes me think... and feel free to duck this question if it's like going way too far out there. But
sure.
I've long been a fan of Apache Kafka as a log-based system. One real strength of that is that it's basically a fire hose for data. It can take a massive quantity of input data and deal with it sort of asynchronously. And I don't think you're trying to replicate that. But one thing that Kafka's been trying to replicate, and I don't think has entirely successfully done it, is build a usable operating database on top of that log-based system.
Yes. So there, I think it is. You say it's not really the same idea. I think it is a similar idea. They're coming at it from like we're going to start from just the logging component of it. And build the database on top. It sounds like, I'm not super familiar with their effort to do that. I certainly have used Kafka in the past. In fact, the original, when we prototyped SpacetimeDB in TypeScript, and the backing store for the write-ahead log was actually Kafka.
Oh, really?
Way back in the day.
Okay.
Yeah, it was actually Kafka. So I'm not familiar with their efforts to do this exactly, but it is the same idea where we're coming at it from like a, hey, we need the data. I guess I would call it like the data reduction, or like sort of like the state of the thing to be materialized, and we need it in memory, and we need the ability to use that, and that has sort of semantic meaning that like this is the current value of this thing. And the log is sort of a thing that we have and is there, but it's a little bit more secondary to the product as it is right now. But there's a lot of cool things we have planned for that. There's no reason you couldn't listen to that log as a stream, that you couldn't publish it to Kafka, that you couldn't run real-time analytics on it, run some kind of streaming algorithms to say like, oh, as I see transactions come through here, I'm going to count the number of different events that are happening, and I'm going to do some various logic based on that. We're not focusing on that so much right now, although we have had some fun ideas there. But it is, I think, a similar dream.
Okay.
To what you're describing.
Yeah, there's been this long push to, I think it was Martin Kleppmann who said, turn the database inside out. Start with an event log and build up an entire tower of database on top of it. Absolutely.
And I think that is, I mean, every database fundamentally is just a write-ahead log. Like, it's a write-ahead log, and then if you really squint, and then they build, various things on top of it. So I don't know of any database that doesn't use that. That's a gross simplification. I think a database obviously is also organizing the data in memory. Not in memory, but just organizing the representation of the data. But a very important property of databases, not all databases, but most modern databases, is the separation of the physical representation and the logical representation, so that you don't have pointers in your database data. That's crazy. Yeah. Then your database would be like stuck on one machine, because that's like where it is physically located on that machine, or you'd have to have the same kind of memory model, whatever that is. That was the original problem that Edgar F. Cobb was trying to solve with the relational model. The thing that I find to be interesting is we did all of that for disks, right? Sort of separating the physical representation from the logical representation. For some reason, we didn't extend that over into memory, for reasons that I can't really understand. I guess in-memory databases do that, but like I argue that even program memory should probably do that, and that you should have sort of like a separation between my program that operates on my data model and the physical representation of my data, and that I could sort of crack open the hood and change the physical representation of the data, but that doesn't actually require any of my other code to be rewritten.
And we have that. Because like if I use java.util.map, I have no idea how that's laid out in memory. I only care about the logical representation.
You have that, yeah. I mean, I would say you have that to a degree, but you can also, in Java, you have pointers in your data, and you don't know it. So, for example, Java is a particularly weird one, because like if I have a class and I have a member of my class and it points to another class, how do I serialize that object? Well, there's not anything I can do to serialize that pointer. I have to like walk the other thing, and so I have to build a program that actually like walks through nodes or represents classes as a graph, and then I have to kind of build out that graph and provide some kind of representation for that. And that is fundamentally weird. It's mixing your program data with how it's physically represented. So even that, the hash table, not so much. In principle, you just have keys and values. But any objects, like objects are weird. Objects are a mixing of your sort of logical and physical data, I would argue.
Yeah, okay. Yeah, I can see that. Especially if you're coming from like an ECS way of looking at things. I would certainly agree with that.
If you're coming from like a C thing, I think it's even more manifest, because your data that you actually are storing is pointers. Like in Java, they kind of put it in the background and sort of, oh, well, there's no pointers here. But in C, like you have an array, and it's an array of pointers. So if you want to serialize that, well, it doesn't make any sense to, if the data moves, the data changes. And I think that's the fundamental difference between them. Like if you should be able to move your data around and not have any of the data change.
Yeah.
That's like a property.
Yeah.
Portable data, I guess you could call that, or something.
Okay.
And that I think is the key component. And that's not true of, for example, Java objects. Like if I were to move one thing from another place, the actual data in my original object has to change because its pointer has to change.
Yes. Okay. Yeah. Yeah. Now I see what you're saying. Okay. I want to pull sort of up into a bit more developer space on this.
Sure.
Let's talk about client languages because that gives a hint of where you're going. You started off in Rust, partly for memory and partly because it compiles to WASM, and that's a useful property.
Yes, technically we started in TypeScript just to make, well, way
Wait,
back.
oh, okay.
When we had Kafka as the engine. And TypeScript is actually very, very fast. What the problem that we ran into there was it wasn't consistently fast. So occasionally it would just take a millisecond to do something, and it was unclear why. Presumably because it wasn't JIT compiled or something like that in the engine. And so we switched to Rust for that reason.
Okay, and now you're coming back to TypeScript and C#?
We're coming all the way back. C#. So we support actually 4 different languages: Rust, C#, C++, and now Unreal as well on the client, and TypeScript and JavaScript technically, because it's just sort of we technically only support JavaScript, but you can write TypeScript for it, and we have a typing for all your stuff.
What makes those the languages you've targeted?
So Rust, because we wrote the database in Rust, and we wrote Bitcraft in Rust. So we originally wrote Bitcraft in TypeScript, where we had the thing which we called zero-downtime, which was the sort of the TypeScript version of that. We rewrote that in Rust because we needed the performance. We needed to be consistent. The client was always in C# for that. If we had a C# client, we were doing Unity, we needed a C# backend. So now we have a Rust backend and we have a C# backend. We wanted to support Unreal because we had a lot of people requesting to be able to make Unreal. So if we're going to support Unreal frontend, we support C++ backend. And then TypeScript is the most popular, or TypeScript JavaScript is the most popular language in the world. And it's really important for web. We have people deploying games to the web. We've had people deploying apps to the web. So we've always had the TypeScript SDK, and it sort of logically makes sense to do TypeScript on the server as well.
Okay. I can see the games angle. Tell me about how people are using it, or how you hope they'll use it for something like the web. I mean, what's the least gamish application of this database?
The least game. So we have, well, I would say the least gaming one is actually not necessarily a web one even. So we've had, we have some enterprise clients, and I wouldn't want to give up exactly who they are or whatever, but we have financial clients that are doing order book matching, that kind of thing. So I have a list of people who want to sell things and a list of people who want to buy things, and I want to find out who's going to buy and sell them in the right order, and I want to match those things and sort of have transactions fulfilled. That is obviously not very games. We've had that for a long time. They're doing it in Rust, so it's actually not TypeScript. You certainly could do it in TypeScript. We've also had people build, like, for example, there's one startup that's doing something like Figma, but for stream overlays. So the idea here is, if I'm a Twitch streamer, I can have my mods moderating my stream overlay while I'm on stream, and I don't have to actually do that. So they will drag in like memes and things and counters and stuff like that, and they will be represented on the screen, and they can move around in real time and all that stuff. It's like a canvas that they can paint on, and that is updating in real time. That's one example of something.
It's a live collaborative broadcast application.
Correct. Yeah, exactly. And I believe they have plans to also allow Twitch chat to interact. Well, I think they do already because they have like polls and things, but maybe even to manipulate the canvas. So you can imagine Twitch chat drawing on the canvas that is shown overlaid on the stream.
Okay. Yeah. And inevitably, given the permissions model you've got, some Twitch streamers get to pay to get more access to the canvas.
Yes, well, that I assume we're not involved in those decisions, but seems like a reasonable thing for them to do.
Yeah, I can totally believe that. Okay, so I think it's time to move on to how one might write something with this. I get the basic model. What does it look like if I say, I'd like to play around with this and build some collaborative web thing?
Yes. So the goal, what we're trying to do, is have this be as simple as possible. A lot of what we've done in the past is make it very, very performant, make it very well designed, correct, and then production ready and able to run our game. We've launched our game, and I think the goal now is to make it as easy to use as possible. And we're doing a couple of things to achieve that. One is we're adding a bunch of templates. So the idea is you should be able to come to our webpage, look at a template, say, like, I would like that template, run spacetime init, the template name, and bam, you have a running application locally. We'd like to do that for web apps. So like a very basic one that you might want to build is like a real-time chat. Maybe you want to build something like Discord.
Yeah.
That's the perfect thing to build on SpacetimeDB in some sense. It's real-time. It's not so easy to build if you're going to do it with a regular server. It's all persistent. You have complex permissions that you need to keep track of that are editable and all of that stuff. So we want to build some example applications that people can just kind of pull off the shelf and really get an idea of like, what can I build with this thing? We want to become more accessible. So we want to do things like support TypeScript, support all of your favorite web frameworks. So Svelte, React, Vue, sort of whatever else is out there that's popular, so that you can just kind of one click drop in, use table, and be ready to go. In Unity, right, we have an SDK that you can just drop in. You can get started there. More tutorials there. We're really looking to improve our documentation. And then one thing we'd also like to dramatically improve is our pricing model. So we launched our cloud platform in March. We actually haven't charged anybody any energy yet. So people have bought energy. They're sort of stockpiling it. Some people stockpile a lot. But we haven't charged any. We wanted to gather statistics on how is this being used before we actually begin charging people. As part of that, we've learned, like, hey, we should just really simplify the model. We're getting very granular here. It's kind of hard to understand. There's not really a point to that. Like, what people want to know is, how much is this going to cost me, fundamentally? Yeah. So we're doing a couple things. We're adding a free tier. So people can just deploy to their cloud version of SpacetimeDB for free and run basic apps, no problem. We're also going to be doing a pro tier. So that's going to be $25 a month. And then you get a bunch of energy, sort of credit every month. So you can just keep spending up to that limit. And then we're going to do a team tier. And the team tier will be like a named organization on GitHub. So you can have your whole startup join, and you can have complex permissioning to allow these people to publish, or these people to do other things like manage users and things like that. And then we're also adding we have already added actually a first-party auth solution called Spacetime Auth. And that's kind of like Firebase Auth or Supabase Auth, or things that people are probably familiar with. Just lets you get started right away. You get auth out of the box. It's OIDC compliant, so you can sign in with Google, sign in with Facebook, sign in with whatever. Twitch. I don't think we have Steam yet, but we would like to add Steam.
Makes sense.
And that kind of thing.
Okay. What's the licensing for the free version if I want to run it locally? And how useful is it?
So,
is that just for development?
Yeah, it's a good question. So it's not just for development. So there's a free main cloud version. That is basically, we're going to run it for you. You don't have to worry about anything. It's going to run on SpacetimeDB cloud. You can deploy your app. There is always the SpacetimeDB standalone variant, which is the one that you can get off of GitHub, and you can run it. We use the business source license, which the way that works is you can use it for development for anything. You can use it in production for anything except a set of things that the developer provides, and I'll talk about those. And then after 4 years, it goes open source.
Right.
So that's the agreement. In summary, the things that we prevent, sort of, we say, like, there's a limit on, is you can only run one node in production, and you can't resell it as a service.
Yeah.
And so let me explain why. We would like to be able to provide the cloud version, the sort of the highly scalable cloud version, and we would really not like Amazon or someone like Amazon to have Amazon SpacetimeDB, and then sort of we've done all the development for it, but they have all the clients, and so they'll bring them there. So that's the reason for that license.
Yeah.
But ultimately, it becomes open source.
Okay. I know there are lots of people out there that dislike those sorts of licenses. I think they're entirely fair myself.
It's understandable. I mean, I think the thing is too, what you don't want to do, what we said we didn't want to do from the beginning is, oh, hey, we're open source, and then realize this business model doesn't work, and then kind of bait and switch people and be like, oh, we're changing the license, which I think a lot of databases have stumbled down that path. And so we had the benefit of kind of looking at that in hindsight and saying, well, let's start a little bit more restrictive. And then if it's like, you know what, we think we can manage this business model, we make it less restrictive. Nobody's upset when you make it open source. People are upset when you migrate it into closed source.
Yeah. It's when you reduce what they can do for no net
and rightly so.
No visible benefit to the user. Right. Yeah.
Correct. It's a change of the deal. The deal is changed.
Yeah. Always for the worse. Always in favor of the companies when that happens.
It can be. One thing I should mention is that we have announced that Bitcraft is going to be fully open source. So the game,
interesting,
fully 100% open source. We're choosing a license. The thing we're currently dealing with there is we, in certain cases, we've used Unity asset store assets. So we have to actually remove them before we can make it open source. Otherwise, we're open sourcing somebody else's thing, which we can't.
Well, that leads me to perhaps a closing question. What's the future of Bitcraft? Because you spent all this effort building up a platform for a game. Is the game still very much at the front of your mind?
So the game is doing quite well for an MMO. We have been selling it on Steam. We are evaluating when it makes sense to go into sort of full release. And the game was always meant to be free to play. So we have in-app purchases. Basically, there's an Empire system where you can have these skins and things, and you can put up banners in your world. And we're trying to make sure that monetization model works. So the game is plugging along just fine. It is hard to imagine, though, that SpacetimeDB is not sort of the magnum opus of the company. There are a lot of companies for whom this has been true. So like Discord started as a game company. I think Slack started as a game company. Unity started as a game company originally.
Yeah.
It just turns out that it's so difficult to build a game that you end up having to build infrastructure that tends to be useful for other people.
I was reading about, who is it? Gabe someone, the guy behind Valve who ended up...
Gabe Newell.
Gabe Newell. He's recently taken delivery of a super yacht. It used to be a game company.
I think he took delivery of the yacht company, if I'm not mistaken. I think he bought the whole thing.
That's because he migrated from games to being a game delivery infrastructure company, right?
Yes. And I think, that's true. There's no doubt that it's a good model. I mean, Lord knows we've paid a good amount of money to Steam at this point. We've definitely helped. We've contributed to said yacht. That's definitely true. But I think that the game is fun. We love our players. The players love the game. We want to make it more fun. But I think that there's just such an opportunity to not have to slog through server software development that's our dream. I really, really, really would like to improve the general user experience of creating multiplayer real-time applications. And so that's what we've got our eyes set on right now.
Yeah. I've built some web applications in the past, which you wouldn't describe them that way, but de facto they are multiplayer real-time experiences. And it's not been fun. It's certainly not been as fun and easy as you are describing. So I think on that note, people should go and try it. And
I think so as well. And I guess what I would say is if you look at some of the most successful web apps, right, very few of them are single player. You've got, look at Figma, right? Look at Facebook. Look at Twitter. All of them are these multiplayer experiences, if you want to think of it that way. And they're real time. MMO, Facebook is an MMO. It's a weird one, and it's a text-based one for the most part. But it is fundamentally massively multiplayer. And I think that is where a lot of the value that people get out of applications is interacting with other people. And it's been so hard. It's very hard for people to get started. We have definitely had people write to us and say, like, we tried to build this thing for years. We always hit a wall at some point, and thank you so much for building SpacetimeDB, because now I can finally get past that. And that is the most rewarding part of this whole thing.
Yeah, I can see that. But also, you've got the game and also plans on the yacht. You're going to invite me on the yacht when you get it, right?
On the yacht, yeah, I'm not sure about that. I'm too busy building databases, so we'll see.
Fair enough. One for the retirement years.
Yes, I suppose so.
On that note, Tyler, thank you very much for joining me. I look forward to bringing you
Thank you so
back
much.
for SpacetimeDB version 3 in a couple of years, right?
Sounds great.
Cool.
Look forward
See
to
you
it.
then. Thank you, Tyler. One thing we didn't get into in that was how this all feeds into agentic programming, because I think that really is changing the way we program. It's also changing how easy it is to adopt new technology, new techniques, like brand new databases. For now, all I'm going to say on that topic is they've been putting a lot of effort into their documentation for humans and for agents. So if you want to give SpacetimeDB a try and see what it's like, now might be the best time. Link in the show notes as always. While you're heading to the show notes, please do take a moment to like, rate, or share this episode. It helps spread the word, especially as we're back for a new year. And we are planning more episodes in 2026, so please stay tuned and make sure you're subscribed. But for now, I've been your host, Chris Jenkins. This has been Developer Voices with Tyler Cloutier. Thanks for listening.